Okay, everyone, I would like to give a quick review of the method of Lagrange multipliers that we learned for inequality constraints. And that we talked about last time, but as a review, let me share this screen with you. Slideshow from current slide. Okay, here we have a problem with right now one objective function. It's always going to have only one objective function, and here it only has one constraint. It has two choice variables, but one constraint. You write it like this. Either the constraint binds or it doesn't. If the multiplier is less than 0 in the solution, like if you try to solve this using the same method as before and you find that lambda is negative, that means your constraint wasn't binding, and it should be ignored. At least set equal to 0 is the best way to think of that, because it still has to hold. I said a lot last lecture that you can just ignore the constraint. It doesn't matter at all. I think maybe more precisely is you set lambda equals 0, and then it will maybe disappear from the Lagrangian. That's a better way to describe it. It still has to hold in the solution. It just won't bind. There's a difference between holding and binding, right? Holding is when the dog has a chain and the chain hasn't broken. The chain is still there. Whereas binding is that the chain is completely taut. The dog is going as far away from the pole, the center as it can, but it can't go any further. That means the constraint is binding, but the constraint holds just means it's anywhere. And when you do a problem like this with a constraint, an inequality constraint, in the solution has to hold. Definitely has to hold. But it doesn't have to bind. And that's sort of what I want to have this practice with. Let's see what happens when you do some problems like this. And then I gave us this very easy example where there's only one choice variable. We found that if you solve it here, you get lambda negative, and that's bad. So you should just set, instead of letting this first order condition determine what x is, you should use this one. Set lambda equals 0, you get x equals 5, remember? But if you take the same thing and say, well, what if instead of x less than or equal to 6, it was x less than or equal to 4, then we have a different result. And in fact, now this constraint does bind, and you do need to include lambda equals 2 in there, and then you have a solution, and x star equals 4 in that case. And it's okay because lambda is positive, not negative. Okay. Then we talked about the complementary slackness condition, which is just a fancy way of saying either lambda has to be 0, or the other part, which is the constraint part, has to be 0. One of those two things has to be 0. That's what it means. And of course, if the constraint part is 0, if the c minus g part is 0, that means it binds. You should look at an equation like this: g of x and y is less than or equal to c. You should by now be able to realize that, oh, if it equals c, that means it binds. If it's less than c, that means it doesn't bind. So the complementary slackness condition is saying either the constraint binds or lambda is 0. Okay. And then we looked at this problem. In fact, I think we did this problem. We found that, oh, lambda is greater than 0, no problem. That means this is the solution. X star equals 5, y star equals 2.5. We did that one, right? And we got to this part where, what do we do when there's multiple constraints and you can't be sure if they bind or not? Well, you can do whatever you want, but my suggestion is, use some method where maybe you start with assuming that they all are binding. See what happens. If you get to a point where one of the lambdas is negative, you're like, well, okay, let's choose that constraint, the one with the negative lambda, and set it equal to 0, and then continue on with the problem. And once again, it'll get simpler when you do that, right? You're starting with maybe a complicated thing with multiple constraints, and then you simplify it there's only one constraint, or there's one fewer constraint. Every time you do this, you're like eliminating a constraint. It should make the problem simpler. Eventually, you'll get an answer if it's a well-defined problem. Okay, that was our method. Am I going too fast? I think this is largely still review, if you remember from the previous class. Okay. Okay. And here's a problem I don't think we actually got to, did we? Maybe we started talking about it, but we didn't solve it. Right? Did we solve this?
No.
Yeah, okay. Let's do this problem. Example 3 from my slides. You guys can help me here and write out the, I have an Apple Pencil, but am I gonna, is it worth switching here? I think I'm gonna just go the old method and write with my thing here. Write out the Lagrangian equation. Can you guys help me here? L equals, what should I write here? So let's take a look. Let's take a look what's going on. This is a problem where we have not one, but two inequality constraints. I've labeled them 1, Roman numeral 1, and Roman numeral 2, lowercase Roman numerals. I don't know why. I see that sometimes. That means we're going to have 2 lambdas. And how should we call them? Well, let's just use subscripts. Call it lambda 1 is the one for this constraint. The corresponding multiplier for this constraint will be called lambda 1. The corresponding multiplier for this constraint will be called lambda 2. Fine. Now we should be able to write out the Lagrangian equation just as before. You want me to do this one, or does anyone want to volunteer? Give this answer. Anyone volunteer? I'm going to do it. Right. The objective function is xy, right? I add something to that, which is lambda 1 times the formula from the first constraint, which is the right side minus the left side. Wouldn't you agree? N minus 2x minus 3y. And once again, let me remind you, the reason you write it this way is so that we can use our rule about lambda. For example, if you had written this backwards, if you said left side minus right side, then all of these, this whole thing would have been multiplied by -1, which means the interpretation of lambda is flipped from positive to negative, which means you would actually have to say, oh, if lambda is positive, that's bad. And it should be negative. And we don't want that. We want to simplify. We want to, what's the word? We want to just have an easy to use convention, I would say. And that is just make sure everything's positive. The lambda will be either positive or 0. Lambda will be positive or 0. This part will be positive or 0. That's good. You get that? And then what do I do for the second one? Just keep going. Add lambda 2. What do I write here? This is a pretty simple thing to write. It's just 2 minus x. Does everyone see how this is what the Lagrangian looks like when you have multiple constraints? Same thing, just do it twice. Just do it again. Agreed? You agree. What do we do now? We're going to actually have 4 first order conditions now. I wonder if I could write them up here. What's Lx? And what's the first order condition from x? Well, it's going to be the partial derivative of L with respect to x is equal to 0. That's what the first order condition is for x. What's the partial order of L with respect to x? Well, here's a y from this first term, xy, that becomes a y. From this term plus lambda minus 2x, we get a -2 lambda 1. I should have said lambda 1. Minus 2 lambda 1. And now from here, we get here's a lambda 2 times -x. That's actually a minus lambda 2, isn't it? And that whole thing equals 0. You guys see? That's the first order condition. Yeah. I'll write these all out, but you don't need to write them all out to solve this. From the second one, we'll get what? X. From the first term, xy, the derivative of xy with respect to y is x. Now we're scanning for y's. Where do we see y? We see one here, times lambda 1 and times -3. That's -3 lambda 1. Hard to draw lambdas sometimes, but I think I got it. And that's it. That's the only place where y's exist. Now you can do one for here. It's like you got a subscript and another subscript. It's a subscript. L sub lambda 1 is, that just gives you the first constraint right back. 10 minus 2x minus 3y equals 0. I have an Apple Pencil and I'm still not using it. It's because I want to write directly onto this screen. Probably could figure out some way to do it. And then L lambda 2. Ooh, that's supposed to be a lambda 2. Undo. This. Lambda 2. That just gives me 2 minus x equals 0. Right, guys? So here are the 4 first order conditions that are relevant for this maximization problem. Agreed? So here's how you tackle a problem like this. In my opinion, here's a good way. Just do what you normally would do, which is solve the system of first order conditions. You happen to get really quickly an answer for what x is. Do you see it? The second one really quickly tells you what x is. It says x is going to have to equal to 2. X must be 2. All right. Well, let's plug that into the third one. See what we get. If x equals 2, that means 2 minus 2 times 2, which is 2 minus 4, which is 6, minus 3y equals 0. So 6 equals 3y, which means y equals 6 divided by 3, which means y also equals 2. Should I have written that out? That's just like arithmetic. You guys okay with that? I get x equals 2 from the fourth one. I get y equals 2 from the third one, just by plugging 2 in there for x. Now I can tell what lambda 1 is from the second first order condition. I can tell what lambda 1 is. You might say, why do I have to bother with lambdas? Those aren't the choice variables. The choice variables are x and y. Shouldn't I just be done here? X equals 2, y equals 2, done. Actually, no. You should still calculate what the lambdas are. And the reason is this method only works. What should I say? This solution is only valid if the lambdas are positive or 0. I should say they can be 0. 0 is a sort of right on the edge of binding versus not binding. That's okay too. Okay, so lambda 1, let's figure it out from the second first order condition. We have x minus 3 times lambda equals 0. Well, we know x equals 2. So 2 equals 3 lambda 1. Divide both sides by, we actually get a positive number here, 2/3, right? I actually don't care what lambda 1 is. All I care is that it's positive, and it is. Agreed? Now let's get lambda 2. This is the last one, and I'm wondering if we won't be able to do this just in our heads. Should we write out this one? Let's write out this one. Let's take the first order condition and plug in what we know. For y, we know it's 2. Here I am. I'm writing Lx again. Lx colon, meaning what follows is another way to describe the first order condition corresponding to Lx. From the first order condition, we plug in 2 equal to y minus 2 times lambda 1. Well, we know lambda 1 is 2/3, so that's 4/3. Oops, this is supposed to be 3. And now minus lambda 2 equals 0. I'm going to move the lambda 2 to the other side and get what? Lambda 2 is actually 6/3 minus 4/3. It's actually also equal to 2/3. What does this tell us? You guys, what's our method? Our method was to just solve this thing like normal. And if the lambdas are positive, then we're done. The lambdas are positive. So we're done. This is the solution. X equals 2, y equals 2. Agreed? I can even put little stars here to really emphasize that, hey, we found the optimal X and the optimal Y. Congrats. By the way, there is a second order condition. You know what? It's actually not a second order condition. It's called a sufficiency theorem that if you're taking this as a graduate course, you know, what we would talk about rather than a second order condition, but an equivalent sufficiency theorem to prove that, oh yeah, indeed, this is the maximum. I'm not going to make you do that in this class. In this class, if you're doing a problem with inequality constraints and you get to this point here where you found answers for the choice variables and you found that the Lagrange multipliers are both or all, however many there are, they're all positive or zero or positive, just not negative, then I'll tell you, you can stop. You can say, great, we're done. I'm not going to make you do any more sort of proof that this is the answer. I mean, you have to get the right answer. You have to have done all the calculus and the algebra correctly to get the right answer. That's not what I'm saying. I'm just saying it's sufficient. It's sufficient for me. Sufficient for me. You guys have any questions about that? How we got here? I sometimes, you know, make a big deal like, oh, we found the answer, hooray. And then I sometimes do these arrows. Oh, that's not the even arrow. Forget about it. Oh, that was a stamp. I want to go. That's what I meant to do. All right, so that's the answer for this one. Do you guys have any questions? Anyone who's here and paying attention have any questions? Maybe I can guess what kind of question you might have, even if you're not saying it. How about, what do we do if lambda is negative? Wouldn't that be a good question? You should have asked me that question. Why didn't you think of that question? No, that's okay. What do you do if lambda is negative? Well, maybe you already know. The answer is set whatever, like let's say one of these lambdas was negative, we would want to set it equal to 0 and redo. Actually, you don't have to redo anything. You can still use the same set of first order conditions that you had, only this time with the new, whichever lambda you found that was negative is now just manually set to 0, and you proceed that way. Okay, so actually I have an example where that'll do that. Let's take a look. I'm going to clear my drawings. Oh, by the way, I do have the answers here. That's the Lagrangian equation. Here are the first order conditions, the same ones that we did, right? Just confirming. And then you solve it. And this is how you solve it. From the last one, you get that. From the third, exactly what I said in words is now what's written in text on the screen. So you can always go back and look at this. Actually, I don't know if I've posted it yet, but I will post this on Blackboard and you'll have access to it. Okay. It's not a secret. I don't want this method to be secret. Like, oh, you don't get to know it because it's my personal information. No, it's available to you as a student of this class. All right. Next example. This is example 4. The only thing I've done, I want to do exactly the same problem. Exactly the same problem. It's going to be boring. You're like, what? We already did this problem. Here's the only difference. X is now, I just changed this 3 to a 2. The only difference is 3 instead of a 2 in the last parentheses here. You see that? That was a 2 before, now it's a 3. I probably should have just left the first order conditions out there. Okay, let's take a look. First step is to solve it assuming both constraints bind. That's to just say, let's take all 4 first order conditions here. You guys want to solve this like ourselves using some annotation? Let's do it. Black. From this one, what do we get? X equals 3, right? You see that? I'm just solving for X. How about from this one? This one we can solve for Y. We get 10 minus 2 times 3, it's 10 minus 6, that's 4. Minus 3y equals 0, so 3y equals 4. So y equals 4 over 3, right? Did I go too fast? I just plugged in x equals 3 here and solved for y. That's all I did. From this one, I think it won't always be this easy, by the way. It won't always be this easy to just sort of solve the first order conditions. These happen to be very simple constraints. I'd like to give you relatively simple problems in your questions on your exams, but because it's a take-home final exam, I think I do have to make it a little more complicated than like this. What I'm showing you here would be too simple for a take-home final. So I'll probably have something with a little bit more, but the method will still be the same. You're solving these systems of equations for x and y in lambda 1 and lambda 2, and then you see what happens. Maybe I'll give you a more complicated example this time. Certainly on next Tuesday, we can talk about that. All right, so we know that x equals 3. So 3 minus 3 lambda 1 equals 0. That's the same as 3 equals 3 lambda 1. I think that means lambda 1 equals 1. Did I get that right? 3 minus 3 lambda 1 equals 0. You with me so far? Lambda 1 now equals 1. I'm getting that by plugging in x equals 3. So far, so good. Everything's been positive. Lambda 1's positive. Let's try here. We get, I'm going to write this one out with y's. I get 4/3 minus 2 lambda 1. We just solved that lambda 1 equals 1. So minus 2 lambda 1 is the same as minus 2. Minus lambda 2 equals 0. I'm going to bring that lambda 2 over to the other side. What do we get for lambda 2? We get 4/3 minus 2. What is that? Negative 2/3. What do we do when we have a negative multiplier? You guys remember what that means? If lambda 2 is negative, then
equal to 0.
Yeah, great. That means, like, if you want to make a big red X here, it's like Family Feud sound. It's wrong. And you set it equal to 0. Perfect answer. Thank you very much. I appreciate it. So instead of finding a solution, we didn't find a solution, but we still made an important step toward finding the solution. And that was to realize that lambda 2 should be set equal to 0. Just force lambda 2 to be equal to 0. Oh, and by the way, eliminate this constraint. It no longer holds. With equality. Okay, so let's get rid of that one. This is the sort of like the complementary slackness. You remember that what I said about complementary slackness? If you know lambda 2 equals 0, that means 3 minus x could be anything. It doesn't hold with equality, so you just ignore it. Did that make sense? That's kind of an important step. We set lambda 2 equals 0. We use the fact that there's complementary slackness to say, well, if lambda 2 equals 0, that means this part here, the 3 minus x part, could be anything. And before we had assumed 3 minus x was equal to 0, and that we can no longer assume. And the best way to treat that in your equations is just to scratch it off or whatever, just to don't include it. I'm gonna erase some of these though. So I wanna make some more progress here. All right. So now what do we do? Well, we have 3 equations, but we have 4 unknowns, but not really. Why not? Because this one here should be 0. This is now a 0. I won't even label it as a 0, but we know that this is a 0. Therefore, it's really like 3 equations and 3 unknowns. We can solve it. And in fact, the way I would say to solve it is to eliminate lambda. Let's do that. Let's write this one in terms of lambda 1. What do we get from this one? Well, lambda 2 is 0. It goes away. If we add 2 lambda 1 from both sides and divide by 2, we get lambda 1 equals y over 2. You guys see how I got that? I set lambda 2 equals 0 because we found it that way. And then I solved for lambda 1 and I got y over 2. Agreed? How about from this one? From this one, we get lambda 1 equals what? X over 3. So here's how we eliminate lambda 1. We just say, well, y over 2 equals x over 3. Good. If you want to write it a little bit, if you want to cross multiply to make it a little nicer looking, you might say 3y equals 2x. I kind of like that. The reason I like that is because I can see, I'm looking ahead and saying, oh, I'm going to have a 3y here. I might as well just leave it as 3y, and then I'll be able to plug that in for 2x. Okay, so take this last one. We get 10 minus 2x. Now, instead of minus 3y, we're going to substitute in the 2x for the 3y. You get minus 2x. By the way, if you're uncomfortable with this, if you wanted to solve for y, you could. It wouldn't have changed anything. You could have said y equals 2/3 x and then plug that in. It doesn't matter. In both cases, you'll get a minus 2x here. Okay, equals 0. Oh, this is enough to solve for x. We get 10 minus 4x equals 0. 10 equals 4x. X equals 4. Sorry, 10 over 4, which happens to be 2.5. Right? Maybe I should write it 10 over 4. Is that a little nicer way to write it? Agreed. We found x. What about y? Y is equal to 2/3 times x. So when you take 2/3 times 10 over 4, is that right? 20 over 12, or why did I write this as 10 over 4? This actually could have been 5 halves. Either way, 20 over 12, that's like 10 over 6. All right. It's like 5/3. Which is 1.6 something. I think. Did I do the math right? Anybody can confirm this? X is 2.5, y is 1.6 repeating. It sounds right to me. But we're not done. You might say, well, why aren't we done? We just found x and y. We already did that mumbo jumbo with lambda 2 and realized that that should be equal to 0. So we should be good there. What about lambda 1? Yeah, I would say you should probably still check what is lambda 1 equal to in this case. It's equal to x over 3. That's 10 4, it's 5 halves divided by 3 is 5/6. Okay, doesn't matter. What matters is that it's positive, and that's like the green check of goodness, right? We have lambda 2 is equal to 0, lambda 1 is positive. Those are both satisfactory, which means we have a solution. This is the solution. Right? So for this problem, when this was a 2, when this 3 was a 2, we got the case that both constraints bind x equals 2, y equals 2. But then when we changed this from a 2 to a 3, like it is here, then we found that this constraint no longer binds and x equals 2.5, y equals 1.6. Do you guys see how that happened? And then the method of Lagrange multipliers actually told us that. We could have figured it out on our own. let's be honest, if we had a graphing calculator and, so if we had some computer know-how to solve a problem like this, we could have done this without the method of Lagrange multipliers. It's really just sort of like a way to organize the process. That's how I think of it. It's like, okay, here's a way to organize everything that could happen and get you to the solution. Do you guys have any questions about this? Which time do we have? It's 1:07. No questions? Can I'll clear my drawings. Oh, by the way, I do have the answer here. Same thing I did with you is written here. Remember, we found lambda 2 equals -2/3. This is an error. Error is maybe not the right word, but it means it's invalid solution. The multipliers cannot be negative. So in this example, lambda 2 is, yeah, it was wrong to assume that all constraints bind. That's what we were essentially doing when we started solving this equation, the system of equations, as if all of four of those first order conditions were holding equal to 0. That's essentially, we were assuming that all the constraints bind, and turns out they didn't. Okay, that just means we need to change what we assumed. And since we found lambda 2 is negative, actually Kai got this right away. Lambda 2 is negative. It's like, okay, set lambda 2 equal to 0. She was paying attention because that's what I had said earlier in the lecture. And that's how you proceed. And here's what it looks like I actually sort of removed, you don't have to literally remove the lambda 2 part of it. You guys get that, right? I mean, even if there was still the lambda 2 part of it, but lambda 2 equals 0, it doesn't matter. It doesn't matter what else is happening here with L. Okay. And you solve this system of equations, you get, yes, exactly the answers that we got. Means I did the math correctly. X star equals 5/2, Y star equals 5/3. That's the correct answer. And you can be done there. This is sort of the last example I have, and I actually didn't write this one out, but it's from this textbook here. Oh, you can't see me. Maybe you can see me a little bit. Yeah, can't see myself, but there's this Cheng and Wainwright textbook. This one is like one of the first examples of multiple constraints, and just let me talk about it a little bit. I think I have some time. This is like a utility maximization problem. Here's a consumer with this much utility. Their utility is x times y squared. And the book describes this first one as a budget constraint. X plus y has to be less than or equal to 100. That's a budget constraint. This second one here is called a rationing constraint. And none of us are old enough to remember because we weren't alive, but there was a time, like back in World War II, I think, that some goods were rationed. And there was a price for the goods, but you couldn't buy as much as you wanted at that price. There was a limit to how much, like bread or anything with sort of rubber products or anything where it had to do with rationing for the war effort. You had to buy it with this coupon. And so here's a case where the coupons give you a new constraint here that, maybe you have 120 coupons, and to buy a unit of X, you need 2 coupons, and to buy a unit of Y, you only need 1 coupon. Therefore, this is it's like a different budget constraint. And the way to get some intuitive sense as to why you might have 2 separate budget constraints is that this one has to do with the money, and this one has to do with your coupons used for rationing. Okay, and then the question is, how would you solve this utility maximization problem given both of these constraints? And I think I actually don't have, oops, there was a little solution there. But we can do this. I'm tempted to want to do it with my Apple Pencil. What do you guys think? Yeah, I'm going to switch. I'm going to switch. Or am I? Stop share. To this, if that's okay. Okay, how would we do this? Should I write the problem again? Or can I just go straight to the Lagrangian? The Lagrangian is, how come it's not appearing? X, is it x y squared or x squared y? It was x y squared. Same. And now we're going to have lambda 1 for the budget constraint. It's like it's really writing harder than I mean. That was 100 minus x minus y. It's very touchy. I'll get used to it. Plus lambda 2. And now we're going to have the rationing constraint, not the budget constraint, minus 2x minus y. Correct? Here's this. So here's the problem. And we want to use method of Lagrange multipliers. There are any inequality constraints. I would say first thing to do is just write out the first order conditions for x and y and lambda 1 and lambda 2. Maybe we need them all. Do we need them all? Yeah, what the heck. For this, we get y squared minus lambda 1 minus 2 lambda 2 equals 0. From Ly, what do we get? And we want to say partial derivative with respect to y of xy squared is 2xy. Minus lambda 1 again. Here's just minus lambda 2 equals 0. Now we have the two constraints. I guess this is closer to what my actual handwriting looks like, as opposed to my mouse writing. Okay, what should we do here to try to solve this problem? And remember, you have some options, but my suggestion is always just proceed like normally and solve the system of 4 equations. It's maybe not that surprising that we don't actually need to look at the first two here, the Lx and the Ly, do we? We can just use the last two conditions to solve for x and y. You see that? These last two don't have any lambdas in them. So let's just solve those for x and y and see what we get. How would you do this? I would say from this one, let's say y. I'm like trying not to touch the screen, but actually I can. Who cares if I do? Y equals 100 minus x. Correct? And we're going to plug that into this bottom one to say 120 minus 2x minus 100 minus x, which is actually minus 100 plus x, because minus and negative x is the same as plus x, equals 0. Agreed? All I've done is substituted y into there, into that last first order condition. Now simplify this. 120 minus 100 is 20. Negative 2x plus x is negative x. Let's just move the x to the other side, and we have an answer. X equals 20. And then from the top, from y equals 100x, we get y equals 80. So we have a potential solution right now. Let's not be so brash to think that we're done because we found x and y. In fact, we haven't used at all the first order conditions about x and y. And those are important. But luckily, this method has a way of like checking to see, is this, by the way, you guys are good enough with like visualizing lines to know like what's going on here, to visualizing these functions. What is x equals 20, y equals 80? That's just the intersection of these two downward sloping lines in the first quadrant of the xy plane. Maybe you can see that in your head and maybe you can't. I can't really tell. I've done this for so many years now that it's like just second nature to me. When I see these two constraints, I just think of them as like, the hypotenuse of a triangle in the positive quadrant of the xy plane. Maybe you guys don't think of them that way, but I do. And then this point here, x equals 20, y equals 80. Well, that's just the intersection of those 2 points. By the way, you don't have to think of it that way. I'm just mentioning it. Okay, so x equals 20, y equals 80. That's so far what we've got as a solution to this system. But the lambdas are what's going to tell us whether that's actually the optimal point. The lambdas will tell us whether you can do even better than this point or not. So let's just plug in what we found for x and y into the top 2 first order conditions to see what the lambdas are. And if they're 0 or positive, then we're fine. If they're negative, then what? Then we should say, okay, whichever lambda is negative, that constraint is not binding in the solution. There shouldn't be binding. We assumed it was binding and we were wrong. So we need to change our assumptions and say, okay, that constraint, the one that's negative, we should now assume it's not binding and set that lambda equal to 0 and then see what the solution to our first order conditions are. Okay? So now let's see what the lambdas are. Do you think we have enough space on our screen to do this? We're gonna, do we have time? Yeah, it's 1:19. We go to 1:45. Let's try to cram it in here. I think I maybe have enough space, especially because I could delete if I wanted. I can delete this equal to 0. I'm going to save myself some space here and say this equals. Okay. I've moved those things to the right side and it's an equal sign now. Okay. And actually these should be arrows and not equal signs. Okay. What I've written now is still valid. Let's plug in y equals 80 and x equals 20 and see what we get. From the first one, we get, okay, 80 squared, that's kind of a big number. That's 64 times 100, which is 6,400. 6,400 minus lambda 1 equals 2 lambda 2. And from this one, we get 2 times x times y. X times y is 16 times 100, or 1,600, times 2 is 3,200. Also minus lambda 1 equals lambda 2. You guys ever do this trick with algebra where you take 2 equations with which are true and subtract 1 equation from the other? Sometimes that's actually a pretty convenient thing to do. Let's do that. Let's subtract the second equation here from the first. We're talking about these 2 equations. I realize I'm running out of space on the screen. I will like make some more space for myself later. Actually, maybe I'll do it right now. Do I want to save? Do I want to save everything on the screen? I'm not sure. I think I have space here. I'm going to subtract the top from the bottom. I get 6,400 minus 3,200 is 3,200. Minus lambda 1 minus a negative lambda 1 cancels out. And then we get 2 lambda 2 minus lambda 2. That's just lambda 2. So actually, I knew this was going to happen. We solved for lambda 2, and it's 3,200, and it's positive. So we can give it like a green check if we want. Ding. That's fine. You want the green checks. You don't want the red X's. Now let's go back and see what lambda 1 is. Well, we can use this equation here. Okay. This equation here, let's plug in 3,200 for lambda 2. And what do we get? We actually get 3,200 minus lambda 1 equals 3,200. That says 0 equals lambda 1. What do you guys think about this? Should it get the green check or the red X?
Check.
Yeah, it's actually okay. It's actually okay that lambda equals 1. You might say, but wait, what about the complementary slackness thing? The complementary slackness says if lambda 1 is 0, that means the other thing could be whatever we want. It could be anything. The 100 minus X, the 100 minus X minus Y could be anything. Okay, yes, but it could actually still be 0. So this is the unusual case where actually they're both 0. Lambda 1 is 0 and 100 minus X minus Y is equal to 0. So complementary slackness doesn't mean one but not the other is 0. Doesn't mean that. It means at least one and possibly both are 0. And that's what's happening in this case. Kai is correct. We can give this a green check. And that means we can give this answer a green check. And that is what it says in this solution. I don't want us to think that this was destined to happen, though. That we were destined to get the correct answer on our first attempt. Actually, it's very possible. Not only is it very possible, but with just a slight change to one of these constraints, with just a slight change to one of these constraints, I think it would no longer would be the case where we happen to hit exactly this point where they're both 0, and then it wouldn't be true that both constraints bind, and then you would have to keep working. You'd have to keep working at the problem to see, okay, which constraint is not binding, set that multiply equal to 0, and now let's go back and forget about that constraint. If it was lambda 1 that was equal to 0, then you would then sort of forget about this constraint. Oh, I erased it. Well, that's good. That's for a fact. Like if we had found lambda 1 to be negative, that's what we would do. We would forget about that constraint. We would set all the lambda 1s equal to 0, so you'd like eliminate them there, and then you would solve accordingly. Got it? Any questions? Okay, man, I think you guys are good. I mean, so let's talk about the homework now. Let's talk about the homework that's due. And I want to help you as much as I can with that, because I don't care. I don't